Now there are certain rules for drawing ray diagrams. Okay, the first rule. Okay, now remember in the last class, this is the first principal focus, this is the second principal focus. Okay, so when parallel rays of light, okay, like strikes the lens, as a result of refraction, it passes through the focus, the second principal focus for a convex lens. Okay, so parallel, okay, as a result of refraction passes through the second principal focus. However, for a concave lens, when a parallel beam of light, okay, passes through the lens, after refraction, they appear to come from the first principal focus, diverging, okay, diverging from the first principal focus. Okay, so in this case it meets, but in this case it diverges, however, from the first. Okay, so this is when the case is for a parallel beam of light, okay, traveling and passing through the lens. In the second case is when light rays pass through the focus. Okay, now when light rays pass through the focus, after refraction, okay, after passing through the lens, as a result of refraction, it will come parallel. Okay, the ray of light will come parallel to the principal axis for a concave lens, a convex lens. Sorry, convex lens. For a concave lens, okay, when a ray of light, okay, seems to be, okay, going to this second principal focus, okay, going to this second principal focus, after refraction it becomes parallel. So this is a case when what? When ray of light passes through the focus. In this case, it passes through the first, then parallel. This also passes through the focus, but it is in the second for concave lens. Then it will become parallel to the principal axis. Remember, the first is for parallel, passes through the focus. The second case is for passing through the focus, and then it will become parallel. But you should know, okay, which focus. You have to be concerned with that. Then the third rule is when we assume the lens to be thin, okay, when the lens is thin, okay, the ray of light, okay, passing through the optical center suffers no refraction, and as a result, okay, there will be no deviation of path. Okay, it will directly pass through the optical center, both for the convex as well as for the concave lens. Okay, so when a ray of light, okay, it hits the passing through the optical center, it suffers no refraction. Okay, now so when we draw ray diagrams, remember, okay, two things. We will take two rays of light coming from the object. Now when like an image is formed, okay, now so we will take two rays from the object. One is the parallel ray of light, okay, you know that it will pass through the focus, and the second is the ray of light passing through the optical center. You need only those two things for drawing the ray diagram for both concave and a convex lens. Okay, so I'll do only a few ray diagrams, okay, for convex lens and for concave lens. So you compare the size of the image to that of the object. You find that the size of the image is quite bigger compared to that of the object. So what happens to the size of the image? It is enlarged. Okay. Then the nature, whether it is real and inverted or virtual and erect, we find that it is erect and hence virtual. Okay, so it is virtual and erect. Okay, now what about the position of the image? Now it is also situated on the same side of the object. Okay. Now there are cases where not necessarily it will be between this. Okay, it might be here or here. Okay, but it will be on the same side as the object. Okay, so as the same side of the object. Okay, so we have this done for the initial case when we have placed between the optical center and the first principal focus. Now you place the object here, okay, at the first principal focus. Okay, after drawing you will find that the image is formed at infinity, real and inverted, and the size is very large. Okay, very large. Then after doing that you go to this, okay, between f1 and 2f1. Okay, you will find that the image, okay, it is formed beyond 2f2, beyond this, and the image, the nature of the image will be inverted, real and inverted, and diminished. Okay, diminished. And then now you go to 2f1. 2f1, you find that the position will form here, exactly here. Okay, and the size will be same. Okay, and the nature will be real and inverted. Now we'll proceed to the case where the object is beyond 2f1. Okay, so this is the object beyond 2f1. Okay, so where will the image be formed? Now you consider just like the previous case, you take two rays. Okay, the first is the parallel ray of light. Okay, so now we compare the image, the size of the image to that of the object. So what do you see? You find that the size of the image is quite bigger compared to that of the object. Okay, so we conclude that the size of the image is enlarged in comparison to that of the size of the object. Now what about the nature of the image? Okay, now you observe that the image is erect. Okay, erect, and also virtual. Okay, virtual and erect. Okay, so the nature of the image is virtual and erect. Okay, the last is the position of the image. Now where is the image formed? Okay, now the image is formed, you observed on this side as that of the object. Okay, so the position is, we write, behind the object. We need not specify, okay, that it lies between this and this or that, okay, because it will vary, okay, but eventually it will be behind the object. Okay, now we have done for the case when the object is placed between the optical center and the first principal focus. Okay, now you shift this object to the first principal focus. Now where will the image be formed? Okay, after drawing, okay, remember the two rays, parallel ray of light and then the ray passing to the optical center. You will get the image forming at infinity, and the nature, it is real and inverted, and the size will be quite enlarged. Okay, very large. Then you move to the case where the object is placed between f1 and 2f1. Okay, now what happens to the image? The image, it will form beyond this. Okay, not exactly here, but beyond this 2f2. Okay, and the nature of the image, you will find it will be inverted. Okay, inverted, real and inverted, hence the nature of the image. And also the size, it will be enlarged. Okay, enlarged. Now we'll move to the case where we will place the object at 2f1, exactly here. Okay, amazingly, the image will form here and the size will be the same. Okay, the nature will be real and inverted. Okay, then I'll place the object here beyond 2f1. Okay, so let's draw the ray diagram when the object is placed beyond 2f1. Okay, consider the two rays. Okay, there are parallel ray of light. Okay, so draw the parallel ray of light. And then, according to the first rule, this will pass through the second principal focus. Okay, when the object is placed beyond 2f1, okay, now this is the object AB, okay, then a ray of light now from this point A, okay, which is parallel to the principal axis is drawn, okay, and according to the first rule, it will pass through the second principal focus. Okay, then the second ray of light is the ray of light which passed through the optical center. Okay, then you see that the refracted rays, they meet at a point. Okay, they meet at a point, and this intersection, okay, of the lines, it will give you for this dip A. Okay, so it will give you A prime. Okay, let's designate it as A prime. Then you extend this, okay, to the principal axis, perpendicular to the principal axis, you will get A prime B prime, which is the image of the object AB. Okay, so now we will compare. Okay, now and we will try to find the position of the image. Now when you compare the size of the object to that of the image, you will find that the size is quite small compared to that. Okay, so what happens to the size of the image? It is diminished. Okay, and then what happens to the nature of the image? Here, okay, it is inverted, and also it is real. Okay, so the nature of the image, it is real and inverted. Okay, and the position of the image, okay, if you try to locate, you will find that it is between f2 and 2f1. Okay, so the position of the image will be between f2 and 2f2. So this is the case when the object is placed beyond 2f1. Now, however, when the object is placed, okay, at infinity, now what happens to the image? Now, after drawing the ray diagram, you will find that the image is formed at the second principal focus. Okay, and you will find that the size is very, very small, okay, diminished. Okay, and then the nature of the image will be real and inverted. Okay, so with this, I have completed the ray diagram for convex lens. Now we will do the ray diagram for concave lens. Now we have taken a concave lens, okay, and the object, okay, placing the object AB, okay, between the optical center and the first principal focus. Actually, okay, at a finite distance, okay, at a finite distance but not infinity, now you will observe that the case will be the same. Okay, now let's first consider for this. Okay, I've taken for this case between optical center and first principal focus. We have taken the object AB, and then likewise the two rays of light. Okay, the parallel ray of light. Okay, after refraction, it will appear to diverge, okay, from the first principal focus in the case of a concave lens. Okay, so it will appear to diverge from f1. Then the second ray of light passing through the optical center, okay, will suffer no refraction. Okay, now what happens is that you find the refracted rays, okay, they meet at a point, and this point will give you the image of this A. Okay, then you extend this, you will get this to be the image of the object AB and mark it as A prime, B prime. Then you compare, okay, the object and the image. The position, it is formed where it is between O and F1, or you can as well say as the same side as the object. Okay, then what happens to the nature? It is erect and virtual. Okay, so virtual and erect. However, the size for a concave, for the image, it is diminished. Now, when you place, okay, the object anywhere, okay, but not at infinity, now you will find that the characteristics, okay, of the image will be the same, okay, for a concave lens. But at infinity, okay, at infinity, when you place the object, now the image will form here. Okay, will form here in the first principal focus. Okay, and the size will be very, very small. Okay, so without touching, okay, the convex and a concave lens, and if being provided to you, now you just place it, okay, close to the writings of a book. Okay, now you will find that you just place it close. For a convex lens, it will be quite enlarged, okay, the size, but for concave, it will always be diminished. Okay, so that is how you differentiate between these two, okay, without touching them. Okay. Now, this concave lens is also used for correcting, okay, those people who are suffering from myopia. Now, what happens to these people who are suffering from myopia is that the far off, okay, the far off distance, okay, is very near. Okay, for a normal person, it is at infinity, but for a myopic person, okay, it will be up to a certain distance. So that's why they use this concave lens, okay, to correct myopia. Okay, the next topic is power of lens. Okay, so what do you mean by power of lens? Okay, now we know that, okay, that convex lens, they converge, okay, the light rays falling on it. But a concave lens, they diverge, okay, they diverge the light rays falling on it. Okay, so power of a lens is a measure of degree of convergence or divergence of light rays falling on it. Okay. In other words, now what does it mean is suppose, okay, if I have two convex lens, okay, if I take two convex lens, okay, now there will be parallel beam of light, okay, falling on the lens, and if this, okay, this is the optical center, if this focuses very near, suppose, okay, here, and this quite far, okay, you can see the distance, okay, of the focal length. Now you find that the focal length here, okay, now it is quite shorter compared to this one. Okay, so what can you conclude is that it converges more strongly, okay, by focusing it nearer to the optical center, this one, this lens. So this, we say that it has greater power than this lens. Okay, so when we say which lens has more power, we say that the one which has shorter wavelength, focal length, sorry, which has shorter focal length to that which focuses quite far from the optical center. Okay, so in the case of concave lens, it's also the same. Okay, but mathematically, power of lens denoted by P, okay, it is defined as the reciprocal of focal length but in meters. That is why the shorter the focal length, the greater will be the power. Okay, and vice versa. Okay, now the SI unit, okay, of power of a lens is diopter, okay, denoted by D, and they measure it with the help of an instrument called diopter meter. Okay, now as you can see, okay, in the case of convex lens, okay, we'll be doing the Cartesian sign convention. Okay, for convex lens, the focal length is positive. Okay, so you put here positive, eventually this is positive, so positive will be positive power. So convex lens has positive power. But in the case of concave lens, okay, it has negative focal length, and hence the power of a concave lens is negative. Okay, so when they say plus, you should know that it is a convex lens, and when they say minus, it is a concave lens. Okay, now however, okay, like in optical instruments, okay, like cameras, like microscopes, okay, telescopes and all, they use multiple lenses. Okay, why they use multiple lenses? It's because they want to get a sharp image, a very sharp image, and also to avoid many defects. Okay, so with different lenses of different power. Okay, so to calculate in such cases power of lens, okay, P. Okay, suppose we have the first lens to be of power P1, the second lens to be of power P2, okay, and then the third lens, and so on. Okay, so when we combine many lenses, okay, say in a camera, okay, you add, okay, the power of lens of each of those individual lenses, then you'll get the power of that particular instrument. Okay, so now, okay, we will be solving the problem regarding this power of a lens. Okay, now it's a very interesting question. The focal length of the lens of a myopic person. They didn't mention here what kind of lens is it, convex lens or concave lens. But okay, I have mentioned that to correct myopia, we use what? Concave lens. Okay, and concave lens, you should remember what power, positive or negative? It's negative. Okay, so solution. Okay, given focal length, okay, F, it is what? 40 centimeter. And in the formula, they have taken focal length should be always expressed in meter. So in meter, it will be like this. Okay, so therefore, and also focal length of a concave lens is negative. Okay, so we write here before this one, sorry, minus, you write to correct myopia, concave lenses used, and then you can write the sign. Okay, then after this, power of a lens, power of lens, P will be 1 by F, then you substitute. Okay, this is minus 40 by 100 will go up, okay, and then this will eventually be 2.5 diopter. So this is the answer to the